Yeah, okay, now I should be audible, right? Okay, thank you very much. So I thank Hongwan Le for inviting me to speak here, and it's nice to visit beautiful historic Prague as well. So I'm going to talk about some story in 7-dimensional geometry related to this group G2 in the title. So let me first, explain a little bit of background results. So what G2 is and what kind of geometry it generates. So the quickest way to say what is a group G2 is to write down this particular form, phi naught, in 7 dimensions. And then a group of linear isomorphisms acts on differential forms. So it in particular acts on 3 forms. And the subgroup, which preserves this phi naught, is happens to be this exceptional Lie group called G2. But this, of course, is not maybe very clear, and may still there will be some questions. For example, why this particular form? The form looks somewhat arbitrary. So to clarify a little bit further what really happens here, I can say that the 7-dimensional space can be given a cross product, anti-commutative multiplication, which generalizes the classical cross product in 3 dimensions. So that's a cross product algebra. And then the group which preserves this cross product structure, G2, is exactly the stabilizer of the cross product. Okay. And the cross product itself, like I said, it's analogous to classical vector product in 3 dimensions, and like vector product in 3 dimensions can be connected to quaternions, pure imaginary quaternions more precisely. So in 7 dimensions, the cross product is related to Cayley numbers or octonions. The pure imaginary octonions form a 7-dimensional space. So that's one thing to make this form a bit less mysterious. In fact, here is another way to write what this phi naught does. So it's a 3 form, totally antisymmetric. It takes 3 arguments. And the way we compute the value is we take a cross product of first 2 vectors and then inner product with the 3rd vector. So that's another way to explain what phi naught is. Okay, so that's the kind of algebraic kind of point. Now, how we proceed to differential geometry. Suppose we now look at a 7-dimensional manifold. We can find the G2 structure on this manifold. It's a reduction of a structure group of a tangent bundle from general linear isomorphisms to this special subgroup G2. So that's equivalent to putting at each point of a manifold the form which is locally modeled on phi naught. So at any point, you can relate it to phi naught using appropriate linear isomorphism. So then we automatically get a reduction of a structure group. Now, it follows from the way we define the G2, the theory of normed algebras, that G2 is in fact a subgroup of SO7. And therefore, a G2 structure is an instance of a SO7 structure, which means that any manifold equipped with this 3 form, G2 3 form, automatically is. So something wrong with the sound? No. So any form, 7 manifold equipped with this G2 3 form. Let's go back. Yeah. Is automatically a Riemannian manifold, has a metric, it also has orientation, therefore it has a Hodge star. Okay, one can then ask, okay, how restrictive is the condition that we put such a form on the 7 manifold? This again is a known question, so it's necessary and sufficient that M is orientable in spin. And again, this way to see it is So G2 is simply connected. And therefore, G2 is a subgroup not just of SO7, but also a subgroup of spin 7 of the double cover. So that shows, for example, that this condition is necessary. If we got a G2 structure, then we got a spin structure and orientation. Turns out this necessary condition is also sufficient. Okay, so we can see that there is a class of 7 manifolds where we can have a G2 structure and put on them a differential free form of this type. The G2 structure in general will have a torsion, and there is a classification due to Fernández and Gray of torsion components. So there are several classes. Probably the one attractive class is when there is no torsion, when the structure is torsion free. And there is actually another class, which is in the title of this lecture, so nearly parallel, that I'm going to talk about. So all these torsion classes can be determined by looking at the exterior derivative d phi and the exterior derivative of its Hodge dual computed using the metric induced by phi. So let me now tell you what is a nearly parallel G2 structures on 7 manifolds. So the defining equation is d phi is some tau, constant tau, times the dual of phi. One can, I think in the abstract, I gave a particular value of tau. What really matters is that tau is non-zero, but one can then use rescaling of phi to make tau a different constant. So exact value, as long as it's non-zero, is not too important. Now one can further show that if indeed this nearly parallel equation is satisfied, then the metric is Einstein with a positive scalar curvature. So in particular, the Ricci curvature is positive definite. And if the metric is complete, then a standard result in Riemannian geometry known as Meyer's theorem or Bonnet-Meyer's theorem says that if M is that M must be then compact with finite fundamental group if we only know that M is complete. So that's a little bit of the implied topology. Now another view on what does it mean that we have a nearly parallel G2 structure. So and also a bit of motivation. So why we look at this class. We can make a Riemannian cone with a cross section given a 7 manifold. Then the resulting cone metric will have a holonomy in spin 7. So a little bit of a significance of spin 7. So we have this model example of a 3 form in 7 dimensions. If we add one more variable and write phi naught wedge, say dx8, and then add the Hodge dual of phi naught. Let's call this resulting form capital phi naught. Then the stabilizer of capital phi naught in the group of all linear isomorphisms in 8 dimensions is isomorphic to the group spin 7, the double cover of SO7. So the fact that we obtain a spin 7 structure on the Riemannian cone on this nearly parallel G2 manifold is not too surprising, but it turns out that if the nearly parallel equation is satisfied, then the 8 manifold with the spin 7 structure, so the spin 7 structure is torsion free, and particularly this phi naught, well, the form phi, pointwise modeled on phi naught, is parallel with respect to this metric on the cone. Okay, now so phi naught generates so there is again a theory of spin 7 manifolds in 8 dimensions. In particular, it's always true that d phi is 0, and we can consider the holonomy of this metric, so a result of parallel transform, so parallel transport using closed loops. It turns out that well, one exceptional case is that if M is a 7 sphere, then the cone is just the Euclidean R8. If not, there are exactly three possibilities. So the holonomy group of this 8 manifold may be a symplectic group of rank 2. So that means the metric is hyperkähler, compatible with the action of quaternions. And then the 7 manifold M that we started with is called 3 Sasakian. Another possibility is if the 8-dimensional cone has holonomy SU4. So SU4 means that we have a parallel Kähler form and a parallel non-vanishing holomorphic 4 form. So that's the defining property of a Calabi-Yau space or Ricci flat Kähler space. So, and the 7 manifold that we started with in that case is called Sasaki Einstein. And finally, maybe the holonomy may be Aloff spin 7. So in that case, the M is called proper. So there is a classification of 3 possible types of nearly parallel G2 manifolds, other than the 7th sphere. Maybe I'll also point out here that these groups that I wrote down, they are subgroups in the increasing order. Right. So, okay, that's a little bit of motivation why one could be interested in nearly parallel G2 structures. So the resulting related structures in 8 dimensions are then parallel. Okay, now let's consider this case of a Sasaki Einstein manifolds. So let's just recall that's when the cone has Calabi-Yau structure. So Ricci flat Kähler. Right, so we'll look at this type.
Sorry, may I have a question?
Yes, please.
To the previous page.
Previous page, yes.
So in this list, all groups are irreducible, but it's possible that there are some products.
Well, I'm assuming, yes, it's a good point. I'm assuming irreducibility
of the holonomy of the cone.
Yeah, of the cone.
Mm-hmm. Okay. Otherwise, if you assume that manifold is complete, M, then this holds automatically, this irreducibility.
Yes, indeed. If it's complete, then finite, and then we have Berger classification. So then
Galott's theorem about holonomy of the cone. So it's if manifold is complete, then cone should be either flat or indecomposable.
Sorry, say it again.
Galott theorem states that if M is complete, manifold is complete,
yes,
then the cone is either flat or indecomposable.
Yes, yes.
Otherwise, it can be decomposable if M is not complete.
No, but in reality, so wait a minute. I think I'm going to assume the completeness because see, this I was giving here the theoretical background, but I will be looking at the particular examples.
Yes, thank you. Thank you.
Yeah. So, okay, let's then look at this case when we have a Sasaki Einstein structure. So the cone then has a holonomy SU4. So the metric is in particular Kähler, and there is, well, for some integrable complex structure. So in that case, if we start from a radial variable, we'll take this vector field, so dr divided by r, act on it by the complex structure, we'll get something tangent to the manifold M. And if we consider the dual one form eta, then this is what is called a contact form. So the defining relation is if we form n times dn to the maximal non-trivial degree, we'll get something which is never 0. So that's a form on the cross section 1 times S, where S is our 7 manifold. Well, actually not 7, but in this case, it's any odd dimension. And also there is a way to write down the Kähler form on the cone. That's half of the exterior derivative of R square eta. Well, like already was probably clear from previous questions, we'll need to make some further assumptions. For example, we call a Sasaki Einstein manifold regular if this vector field J applied to the R integrates to a free S1 action, so circle action on this manifold. So in that case, S becomes a principal circle bundle over a manifold of dimension 2n. So we call it X. So this X, one can prove that this is Kähler Einstein with positive curvature. And moreover, this first term class or Euler class can be given by the Kähler form. So in other words, it's almost a definition of Fano variety. So first of all, a Kähler positive curvature manifold then will have to be simply connected. So it has a positive definite Ricci form, and that's one of the equivalent ways to define a Fano manifold. So more traditional definition comes from algebraic geometry using the canonical bundle, which will have to be ample, but this is equivalent. Okay, what does it all have to do with the G2 geometry? So if now n is 3, so dimension of S is 7, then so there is a result due to Alexandrov and Semmelmann that one can write down a family of nearly parallel G2 structures which induce this given metric G. So that's the formula in blue. So shows how to write the 3 form. So we use, so capital omega is pulled back by the bundle projection of the Kähler form on X. Capital omega is sometimes called the horizontal Kähler form, because it's not a Kähler form in the usual sense since we're in 7 dimensions, but it's induced from 6 manifold. And phi, so recall the 8-dimensional cone is Calabi-Yau, so it has a non-vanishing holomorphic 4 form. So we take interior product with the radial tangent vector, we'll get something which is 3 form, and it's well defined on the cross section S times 1, which we identified with S. So the right-hand side therefore makes sense. And for any value of a real parameter T, this is a well-defined 3 form of G2 type, and the resulting G2 structure is then nearly parallel, as defined before. Okay, so now okay, I'm going to talk about a special class of 3-dimensional submanifolds that can be defined for any 7 manifold with a G2 structure. So first of all, here is the definition of associative. So if we restrict phi to any 3-dimensional subspace of a tangent space, we'll get something which in general will be less or equal than the volume form. In fact, let me write this displayed formula in a slightly eraser. So
you can put
I can put another one. Yeah. So just to comment on this displayed equation, the model calculation using phi naught is that if we start from any orthonormal frame of 3 vectors, so v1, v2, v3 are orthonormal, then evaluation of phi naught on this triple is less or equal than 1. So in more invariant notation, it's I'm saying that this displayed equality in general could be inequality. It would be less or equal. So if the submanifold Y is such that equality is attained at every point, then we say that Y is associative. Another significance of the associative condition is that when if here we have equality. That implies that V1, V2, V3 are subalgebra of the 7-dimensional cross product algebra. So this subalgebra, of course, will be isomorphic to vector product algebra in 3 dimensions. So that's the condition of associative threefold. If in addition phi is closed, then we actually get an example of a so-called calibrated manifold, a concept introduced by Harvey and Lawson. So if Y is also compact, there is an easy argument using essentially Stokes' theorem that Y is necessarily volume minimizing in its homology class, and therefore it's minimal. So it's slightly stronger condition, so not just minimal, but minimizing. However, we didn't assume that d phi is 0. Instead, we assume that d phi, so just to remind, is tau times the dual 4-fold, where tau is a real constant, right? So not, so we don't use this. So therefore, in our geometry of nearly parallel structures, G2 structures, the associative submanifolds are not calibrated, but the little miracle is they're nevertheless still minimal. The reason is if we put a cone on Y and we get a 4-dimensional submanifold in 8-dimensional cone on M, that actually will be a calibrated 4-dimensional submanifold with respect to the spin 7 structure induced by the nearly parallel G2 structure. And therefore, that 4-dimensional submanifold, okay, it's not compact, but it's kind of, with respect to local perturbation, is volume minimizing. So it's minimal. So its cross-section on the cone will be, so that's our Y, it's still a minimal submanifold. Right, so what I'm saying is on a nearly parallel G2 manifolds, associative submanifolds are not necessarily volume minimizing, but they're minimal. And of course, this is a bit easier than constructing general minimal submanifolds, which involves solving a order 2 nonlinear partial differential equation on vanishing of minimal curvature. So that's another good reason to be interested in nearly parallel G2 spaces. Now, a bit more is true to make this last remark a bit less arbitrary. So there was, I mentioned this Fernández great classification of G2 structures. So the two classes, the largest kind of general family of G2 spaces where every associative is minimal is exactly the union of, well, nearly parallel ones and torsion-free ones. So these are given by equation that d phi is 0 and d star phi is 0. Right, so in this last case, of course, they are minimal because they are calibrated. So here they are minimal but not calibrated. Okay, so that's the significance of the special class of 3-dimensional manifolds. And now I come to, well, so far I was reviewing something that was already known recently, or some things were kind of a number of years. The actual project that I did with my co-authors is, well, we started with a bit of a case study. So first of all, we look at this again, Sasaki Einstein 7 manifolds. So suppose that our nearly parallel G2 structure comes from a Sasaki Einstein structure, as explained on the previous slide. So then actually, there are two particular types that occur as associative submanifolds. They are known as invariant submanifolds and special Legendrian submanifolds. So, and both are easiest way to define is to consider a Riemannian cone again. So a cone on Y for invariant submanifolds means that the 4-dimensional submanifold in 8-dimensional cone is a complex surface. And special Legendrian means that the cone on, in 8 dimensions is a special Lagrangian. Okay, so in particular, invariant corresponds to invariance under this integrable almost complex structure. So here is then the first result. So we assume that S is a regular Sasaki Einstein 7 manifold. So in particular, it has this free circle action, makes it a S1 bundle over Kayla Einstein projective threefold with a Kähler form that's noted by omega. And it satisfies this relation that the eta, the contact form, is a pullback of omega. And consider the induced S1 family of nearly parallel G2-3 forms. So then if we start from any complex curve in a 6-manifold or complex 3-fold X and consider a pre-image in 7-dimensional manifold S, that will be an invariant minimal associative with respect to this G2 structure phi t for any choice of a real parameter t. So that's a little bit, the proof involves essentially a bit of a kind of traditional differential geometric inspection. So we consider the details of how the G2 structure, the G2-3 form is defined, and check that indeed it restricts to Y sigma to give this maximal volume form. Now, moreover, by construction, we can see that this 3-dimensional submanifold is invariant under this S1 action, given a principal bundle. And every deformation of a complex curve will induce a deformation of the respective associative 3-submanifold. So here are kind of examples that can be obtained from this previous proposition. We can take X to be a product of 3 copies of complex projective line, take the Euler class to be the sum of respectively generators of second cohomology of CP1, each factor. And in that case, this Sasaki Einstein 7-manifold S is has a traditional notation Q of 111. At least that's what I saw it, how it's denoted in physics. And well, we also can write it algebraically as a quotient of product of 3 copies of SU2 by a subgroup of U1 times U1. Right, so I think it's probably clear which subgroup would mean. So U1 times U1 will not have a determinant 1. So the last element on the diagonal will have to be determined in order to make a subgroup of the product of SU2s. Okay, so another variation of this example, we can replace this factor of, so instead of this CP1 times CP1, we can put a del Pezzo surface. So the blow up of CP2, an appropriate number of points. Take the Euler class again to be given by the Kähler form. So we assume we take a Kähler form whose cohomology class is integral. So then, yeah, take a sum of this generator on CP1 and the integral Kähler class on del Pezzo. And well, then again, we'll get the hypothesis of a proposition, and we'll get a 3-dimensional associative submanifold. So sigma would be CP1 times a point, and minimal associative will be a 3-sphere. So it's a S1 bundle over CP1, but it's topologically non-trivial. So it's not a product, but instead it's a 3-sphere. A bit more generally, one can replace this sigma to be instead a graph of a holomorphic mapping from CP1 to either del Pezzo or to a product of 2 CP1s. And then ambiguity of choosing these examples corresponds to a generic choice of 2 rational functions of 1 complex variable. Right, so that's a kind of explicit examples how we can construct minimal submanifolds, associatives, in nearly parallel G2. Okay, now here is a next result. So again, we start from a regular Sasaki Einstein 7-manifold with contact form eta as before. We look at the structure of a S1 bundle over a complex 3-fold, X, Kähler Einstein Fano 3-fold with Kähler form omega. Consider the corresponding 1-parameter family of nearly parallel G2 forms. So then the following statements are true. First of all, so this time it's a result about Legendrian submanifolds. So whenever we have any special Legendrian submanifold in our S, if we restrict our fiber bundle to Y, then it's a finite covering of a Lagrangian submanifold of X. So Lagrangian with respect to a Kähler structure. So it's kind of necessary condition for Legendrian submanifolds, special Legendrian submanifolds. Next one gives a kind of a converse. Suppose we start from simply connected Lagrangian submanifold inside this Kähler Einstein Fano threefold. If it's simply connected and three-dimensional, then it must be topologically a three-sphere by Poincare conjecture. So then this three-sphere lifts to S1 family of Legendrian submanifolds in our Sasaki Einstein. So in such a way that, the restriction of bundle projection gives us a diffeomorphism. So here, of course, the non-trivial thing is that, we can locally lift it. It's rather easy to see that we get a local diffeomorphism, but the non-trivial claim is that we get a compact pre-image of the lift, but there is ambiguity. We got S1 family. We need to choose a starting point of the lift and then obtain minimal associative. And one more statement in this result is how else we can obtain examples of minimal associatives. Suppose we got a isometric anti-holomorphic convolution of the Kähler-Einstein Fano threefold. If it has a non-empty fixed point set, then this is a Lagrangian submanifold, and it diffeomorphically lifts to a special Legendrian, hence minimal associative submanifold of S. So if we can find an anti-holomorphic convolution in six manifold, then we can lift it to Sasaki Einstein. Okay, so again, some examples. Let's go back to this 7-manifold Q111. So maybe just to remind what it was. So here, this space. Okay. We also will, so that's one specific manifold we consider, and the other one is S1 bundle over product of complex projective line and del Pezzo. So then we have a, first proposition is about Q111. So we consider three-dimensional torus, so defined by this angle variable, fixing it to be pi over 2. So in the spherical coordinates on X, so on each copy of S1, each copy of S2, we consider standard spherical coordinates. And so phi is the one which ranges from 0 to 2 pi, the longitude coordinate. Okay, so then product of three circles gives us a three torus. Then we can lift it to a family of minimal Legendrian three tori sorry, there's a misprint here. This M should be, of course, the Q111. In a 7-manifold. So for each choice of parameter S, this three torus is associative with respect to this nearly parallel G2 structure. And again, we are free to choose parameter T arbitrarily. Right? So previous examples produced the associative three spheres, and these are associative tori. If we instead consider S1 bundle over CP1 times del Pezzo, we can do a special case when del Pezzo is P3. So this is important point is that P3 is known to be a toric variety. It has a C star action of multiplicative group of complex numbers, non-zeros, and it has a Kähler-Einstein metric, which is preserved by this action. So that allows us to make a anti-holomorphic involution, and then using previous theorem, we conclude that there exists a minimal associative 3 torus in a nearly parallel G2 manifold. So this S3, which is CP1 times P3. So anyway, this assumption on the Sasaki Einstein is as before. So we use the S1 bundle over CP1 times P3 and choose the class. Choose the first term class over S1 bundle to be given by the Kähler form. Right. So the key point here is a toric variety. Now, another class of examples has to do with the so-called Aloff Wallach spaces. So these are compact, simply connected 7 manifolds. They're defined algebraically. We take a quotient of SU3 by a subgroup of diagonal matrices. Diagonal elements are e to the ik theta, e to the il theta, e to the im theta. So the parameters we have to choose is k and l, as we see in the notation for the Aloff Wallach spaces. So these are integers. K is positive, L is non-zero, K and L must be co-prime, and then M is determined by K and L. So the K plus L plus M is 0. So we have a well-defined subgroup. And the subgroup, matrices depend on theta, therefore the subgroup is indeed isomorphic to a circle. Right, so one can check that the resulting quotients are simply connected. Now, one can use the Lie group structure, more precisely use the basis of left invariant 1 forms of SU3. So 1 will be corresponding to this circle subgroup. So there will be a basis of 8, but we disregard the one which is determined by the S1 direction. We get 7 well-defined forms of the quotient. And we use that to write down the family of homogeneous co-closed G2-3 forms, depending on 4 real parameters. So then there is an equation on these parameters to make sure that the G2-3 form is nearly parallel. Turns out that for a generic choice of K and L, there are up to homotheties exactly 2 genuine different choices of parameters, so that we can put proper nearly parallel G2 structures on Aloff Wallach space. So recall, proper means that the cone on this W manifold has a full holonomy spin 7. So this statement I just said is in fact a result found in a paper of Cabrera, Moner, and Swan in 1996. Okay, so what about, so what happens when K and L are not 1 and -1? There is another view on the Aloff Wallach space. It's a fiber bundle over SU3 quotient U2. So the subgroup U2 is consistent of block diagonal matrices. So one block is, we take SU2 matrix multiplied by complex number of models 1, and the remaining 1 times 1 block is determined so that we get a determinant 1 of the 3 by 3 matrix. Right, and then it's easier to see that we get this well-defined map pi. It turns out to be a fiber bundle. Fibers are spherical space forms, a quotient of S3 times by the finite cyclic group, which depends on the parameters K and L in Aloff Wallach spaces. Right, so that's in all cases except this 1 - 1. So I'll tell you about that exceptional case a bit later. Now, another thing is this vibration is not unique even if we fix K and L, because we can again use the theory of Lie groups and algebras, and more precisely the Weil group of SU3, which has an element of order 3. It induces diffeomorphism between apparently different Aloff Wallach spaces, so WKL and WLM. So one can compose our vibration with this diffeomorphism and gets a different vibration. So in other words, several apparently different Aloff Wallach spaces are in fact diffeomorphic. So the same manifold, we get different choices of fibrations. Okay, so this kind of a geometry. And now the result we got is, so okay, assume that this phi W is homogeneous left invariant near parallel G2 structure that we just described on Aloff Wallach spaces. So we assume that K and L are generic, so not 1 plus minus 1. So then the fibers of this fibration are embedded minimal associative threefolds. So here we get minimal spherical space forms with respect to this nearly parallel proper G2 structure. So furthermore, for sufficiently general K and L, we get 3 different 4-dimensional deformation families of these minimal associative spherical space forms. So having to do with this ambiguity of choosing a fibration. Now, what about these exceptional values of parameters? So if we take 1 and minus 1, then first of all, there is only one homogeneous nearly parallel G2 structure. We still get a fibration map, but the fibers are not spherical space forms. Instead, they're S2 times S1. Right, so that kind of a correction, but then the rest of the results goes through. If we use plus 1 and plus 1, then we only get associative well, S3 over Z2, so RP3, for one of the 2 homogeneous nearly parallel G2 structure. That one is 3 Sasakian. So the cone is in fact hyperkähler rather than spin 7 manifold, right? But while we were kind of working on this project, I think it's almost at the same time, Bol and Modnik also studied these Aloff Wallach spaces, W11. They constructed different associative threefolds. And thankfully, it turns out, well, they wrote to us, but we found that our results don't overlap, but rather complement each other. So Bol and Modnik found associatives which are S1 bundles of a compact surface of any positive genus. Right, I think that's probably correctly almost everything that I wanted to say here. Yeah, but it's not the last slide yet.
No, I only want to ask that you have different 4-dimensional deformation families. That means that existence but not uniqueness. Yeah. That means that you, of course, how to say?
No, the different space forms, meaning that you get different value, like K plus L modulus need not be the same as modulus of L plus M. So therefore, it's topologically different manifolds. And yeah, each one has its own deformation family.
So because on each VKL, you have the 2, how many nearly structure? How many nearly G2 structure on each VKL?
In general, there are 2.
2.
So that's, let's go, it's a previous slide what I was talking about. So, yeah.
You have the 4 family or what?
So we start from left invariant forms.
Yes.
So we know, again, from general differential geometry, they're differentials. That will be a wedge product of those 1 forms. So we form some arbitrary looking linear combination depending on 4 parameters. And the way we form it, it's easy to check that at any point we get a 3 form, which is a G2 type. So that's already a G2 structure. But then we have this differential equation nearly parallel. So we compute d phi, express the result in terms of what kind of form of phi we use. So that gives us algebraic equation on these 4 unknown real constants. Turns out that it's solvable and has generically 2 solutions.
Yes,
so that's 2 nearly, yeah. Nearly parallel G2, yeah.
Associative for each nearly.
No, for 1. We consider, we choose one and then work with it. So no, it's not for two simultaneously.
Yeah. So that means that I still do not understand. So it's really C2 structure on PKL.
Yeah.
For parameter family.
Yeah.
Yes.
Yeah. Okay, so right, let's go back to this. Oh no, wait a minute, wrong direction. So yeah, right. So one has to worry a little bit about some exceptional values of the parameters. So there's a generic case, and well, these cases 1, -1, 1, +1 are known to be different. You get topologically different fibers.
So I ask also more questions. So that you say that for each nearly Taylor structure, you have for parameter family of the minimal associative spherical space form. But they are the only one. I mean, any other of the minimal associative sphere.
No, they're not minimal associative spheres. Minimal associative space forms.
Yeah.
Spherical forms.
Okay.
So yeah, they are kind of yeah. Maybe I almost was going to get to this point that you probably also asking. Let me just show you. I think that's one last page of the slide. First of all, what I already said, of course, doesn't bring the story to the end. You can see that the results essentially were started with the case studies. We can see that some well, types of known nearly parallel G2 manifolds, and we're able to find examples of minimal associatives, which are spheres or tori or spherical space forms, which again are probably the kind of three manifolds that naturally will first come to mind, like can one do that? But it looks like one can, with further work, try and produce more examples. But in particular, we can use more ambient 7 manifolds. So for example, del Pezzo times CP1, use del Pezzo 3 because that one is known to be toric, and that helps to find anti-holomorphic involution. In general, it's known which del Pezzo have Kähler-Einstein metrics, and therefore product with CP1 will have Kähler-Einstein. But the problem is those Kähler-Einstein are given implicitly via existence result. So it's one probably needs a little bit more ideas to figure out whether one can find the anti-holomorphic involution or some, well, other sufficient conditions that we have. Or, well, maybe there are further methods to get minimal associatives. Similarly, in Aloff Wallach spaces, Wallach Morning found some examples of one topological type, we found some others, but so far it's again like we're trying to pick up some topologically known types of minimal associatives. Obvious interesting question is to try, based on this example evidence, to see whether one can come up with more systematic general theory, which will produce perhaps implicitly more examples, including those we already found as, well, special cases. So, well, that's kind of what I would hope to maybe eventually say something about these open questions. But as far as today's talk is concerned, I think that's what I wanted to say. So thank you very much.
Is there some more question from audience? Okay, I ask you that of course that you know the program of the counting associative submanifold. So that should be the same question in the nearly G2 manifold, but
well, I'm not aware of even a good conjecture here, but if we really want to do the counting, we want the associatives to be rigid.
yeah.
Those that are a bit easier to find in examples often come with deformation families. Although I would expect that under other general condition, one can say that arbitrary small perturbation of this 3-form phi will make, will change this, probably will result in, so you fix some particular member or family, that one will become rigid. So its deformations will disappear. But again, I didn't try to prove this in a nearly parallel setting. We have a result in another earlier paper, but that was a different type of G2 structure. So one would need, need first of all to some sufficient condition when one can make these associative rigids, and well, then one can count them. But of course, there's a whole list of questions how to count them so that the result is independent of arbitrary choices. For example, suppose we generically perturb phi so that our rigid associatives remain rigid, and repeat the count. You see, the thing is, it may happen that some associative will split into two rigid ones or will disappear. Again, we don't have a theorem saying that it's impossible. So maybe one can make such invariant, but it's currently we're rather far from even making a conjecture.
So it could be harder or that's easier or the same difficult as a counting associative in G2.
In parallel, yeah, but again, that one, there are some non-trivial results in that direction, but I'm not sure that there is already a finished theory with invariants.
So
Then, of course, other great invariants defined differently.
So there are some kind of the elliptic invariant for nearly G2 manifold or something.
You'll have to remind me what nearly G2 is. As I was mostly studying.
Associative is also elliptic or the counting solution of the elliptic equation. Yeah.
Oh, you mean nearly parallel to the same as here?
Can you find some kind of not only counting associative but some non-trivial invariant of nearly G2 manifold?
I don't know. The short answer, I mostly studied actually the parallel ones, but this is the only instance when I was tempted to look at the nearly parallels. Mostly,
if you move to nearly, that is brings the question in in the parallel, it's easier or it makes no sense.
Yeah, I'll probably to answer this question, I'll need to think a little bit more generally about this class. So far, we were looking, maybe to say something on the positive side, of course. So what I presented in this talk is the results from a paper, but not all the results. In fact, the paper has the results of two kinds. So either about these submanifolds, or also results on formality of these spaces, but that probably would better be in a separate talk. So that seems to be a bit better understood, but well, that's another story.
Okay, if there are no more questions, let us hang the speaker again.